Hello Chemie 330 students. Today's example covers the Bernoulli equation. We're going to apply the Bernoulli equation to a stream entering a CSTR through an overhead nozzle. We want to find an expression for the diameter of the nozzle given the volumetric flow rate of the inlet Q, the overall tank dimensions, the steady-state fluid height, and a relationship between the final inlet cross-sectional area and the cross-sectional area of the tank. For the Bernoulli analysis, we'll call our nozzle point 1, and we'll call the point where the inlet stream meets the reactor bulk 2. To apply the Bernoulli equation, we'll have to make sure that some assumptions are valid. The first is that we're dealing with an ideal fluid. We'll assume this is valid since our fluid isn't interacting with any solid surfaces. The second is constant density, which is a valid assumption assuming that our feed is mostly water at constant temperature. Steady state can be assumed since we know that our reactor is operating at steady state. And now we can apply the Bernoulli equation to our inlet stream. We start with the general form of the Bernoulli equation between 2 points. Both points are open to the atmosphere, meaning that the pressure at both is equal to atmospheric pressure P0. This allows us to eliminate P1 and P2 from our Bernoulli equation. Since ρ is constant and our pressure terms are now eliminated, we can cancel the density in all of the remaining terms. We can substitute volumetric flow rate divided by cross-sectional area for our velocities at each point. We know that the height at point 1 is equal to the overall height of the tank, and that the height at point 2 is equal to the steady-state height of our reactor bulk. We are given that the cross-sectional area at point 2 is equal to 1% of the cross-sectional area of the tank. So we can substitute for A2 in terms of the tank diameter, and we can substitute for A1 in terms of D1, the nozzle diameter. This gives us an expression solely in terms of Q, tank dimensions, and our desired value D1. At this point, all that remains is to simplify and get an expression for D1. We start by combining both of our height terms on the right-hand side. We then multiply through by a factor of 2. We can take the square root of both sides, multiply by the term containing D1, take a second square root to isolate D1, and finally, multiplying by a factor of 2, we arrive at the desired, if somewhat unwieldy, equation for nozzle diameter.